The next speaker is Adam Nagel. So Adam Nagel is a co-founder of P1 AI, that the company founded in 2024, and he serves as the head of engineering there. You know, the company CEO is also famous former Airbus CTO, Paul Ermenko. And you know, prior to starting P1, Adam led digital engineering initiatives at Airbus, at Raytheon, and was a CTO of an MBSE tooling startup that worked with aerospace, defense, and energy, as well as electronics industries. So, you know, welcome, Adam, and you know, we are all excited to hear what you have to share with us.
Yeah, thank you. Thank you very much for having me, and thank you very much for making the time. I appreciate it. So as Joseph said, I'm from P1 AI. We're based in the United States, and I'm going to talk to you about systems as code for AI reasoning. I think building on kind of what Michael said in the last presentation, I'm going to show you not just something about machine readability, but actually machine-only usage of something like SysML. So what are we up to? At P1, we are working on building Archie. Archie is an AI agent and engineer that we're designed to be capable of quantitative and spatial reasoning about physical products. The idea is that Archie, as an agentic AI, is doing cognitive automation of what the human does. Archie is hired on to existing engineering teams, so it joins a group of engineers that are working together. Archie interacts through Microsoft Teams or Slack or the work management systems that people are already using. And Archie accesses the same information systems, uses the same tools, and produces the same work products. So the goal for us with Archie is not to replace the way people do simulation or create new CAD tools or subvert PLM or things like this, but actually to put another engineer in the chair with teams to help them deliver more work and to work faster by doing things the same way they do today. We're working on a variety of systems. We have active pilots with a company in the data center cooling space, designing air-cooled chillers like the one you see in the bottom left. We've talked with companies doing generators. A lot of us in the founding team have backgrounds in aerospace, and so we're looking forward to working in aviation and defense as well, and then going on to build even more complex things after this. Now, the subject of this brief talk is going to be, how does Archie think about the systems that it's working on? How does it understand what is in scope for its task? What are the parts it needs to manipulate, and so on? And to talk about how SysML comes into this, I want to go back to kind of what were the insights that led to Archie and P1 that I think rhyme a lot with the last two talks. One is that model-based design these days looks a lot like code. And large language models are great at code. They're trained on quite a lot of it, and you can find people arguing about code on the internet since before the web was invented. So there's plenty of training data. So if you think about something like Modelica, which is a language and ecosystem for doing kind of a differential equation-based analysis of physical systems, it has an object-oriented language that LLMs are pretty good at understanding and writing and manipulating, and then using the compilers and simulators for. Similarly, we have SysML v2 emerging in the last few years, and even older systems like PSpice still have a textual syntax that is well understood and that LLMs are pretty good at dealing with. An additional challenge for training AIs is that you need to provide a verifiable domain, like a way for the AI, if it proposes a change to a design, to understand what are the implications of that, and did that move me closer to or further away from my goal. And going from a design representation like what we see in SysML to something like Modelica to then computing a performance vector gives us this feedback loop. Now, simulators are not infallible, right? You can always lead into strange corner cases, the solver can fail, or you get out of bounds of the models. There's a lot of nuances to this, and we've been doing this kind of thing for a long time. So it's more complex than it sounds, but it does give you a way of anchoring things and giving the AI a way to learn in a way that is grounded with some kind of real performance. So just to give an example of the kind of thing Archie would need to do, in the early phases of our company, we started by working with residential air conditioners, partly because there's so much data available in public. And we ended up actually modeling this one that's outside my window here at home. For an air conditioner like this, common engineering tasks in these companies are like improving the efficiency by a certain amount. Environmental efficiency standards are going up. We need to increase our efficiency to meet the standards next year. There might be creating multiple size variants for a product line. So a product line of these might range from 1.5 tons of cooling power to 5, and then they want to create multiple ones in between while maximizing reuse of parts. You might need to replace obsolete components or reduce your bill of materials costs. This is the kind of bread and butter stuff that engineers spend their time doing at companies that design these systems. So for Archie to be a good member of this team and to help people do this, it needs to be able to perform quantitative intuition and reasoning. So it needs to know, hey, if I'm trying to increase the efficiency, these are the levers I can pull, these are the changes I can make, and here's the second order effects of those. Arch should be able to use engineering information sources. It needs to check data sheets, look up availability and pricing in SAP, look for things in the network drive, stuff like this. It needs to reason about requirements, like business requirements, like manufacturability or regulatory requirements, and then it also needs to explore its options and produce the right work products. So how can Archie make sense of all these things when it's working? Like how does Archie dream of systems? There's all these different data sources that things are going to come from. The reality in most industrial companies is they don't have perfectly formed, perfectly detailed single sources of truth. You can learn about the entire system. So if you look at the desk of an engineer who's doing this kind of work, they have 2 monitors full of stuff, spreadsheets, data sheets, websites, the PLM system, ERP, all these things. And Archie will need to do the same in order to produce like altered product structures or produce the other work products that people are expecting from him. So what is in that mental model and what is the best form of that mental model? One interesting thing to note is that it's not really necessary to have complete knowledge of every single thing in the system, like every nut and bolt and screw and paint and sticker. Actually, you want to load in the information you need to do the task at hand to produce your output and then move on. So it's a partial view, but it needs to be a consistent one of what it's working on, just like a human. So one naive way we could do this is we could just take all those data sources, convert them all into text, and then just plug them straight into a language model, like straight into the conversation. It goes into the context window and the LLM thinks about it as it does work for us. This can work for very simple cases, but in our experience starts to fall apart pretty quickly as you get to more complex inputs or larger inputs. And some of the things that you run into are finite context windows. As you add more and more things to the context of that LLM conversation, its reliability starts to suffer, and so does its performance. Hallucinations, so getting things wrong or making things up. It's not very efficient. You have to carry all this text around with you all the time. And the cross-session durability is not very good. So if I put down this project this week and pick it up next week, I have to load all of these intermediate steps and all of this text back into context for me. And I would note that humans are not great at doing it this way either, at just consuming all this stuff at once. We produce notes, we produce distillations, we fuse these things together in our mind. And that's how we do it. And that's why techniques like MBSE are so powerful. So that's the way that we actually have Archie building its mental model of what is the system and what is the context I need to do my work right now. So Archie actually in its mind creates a semantic graph of the elements it's seen, how they're related together, and how new information merges with that. Now, what are desirable properties of this graph? It really could be any kind of semantic graph, but ideally it should support engineering concepts and really have ideas of requirements and parts and relationships and different domains of interaction and things like this. It should be something that can be incrementally constructed or composable. It should be based on existing standards so we can make the best use of other tools and things in the ecosystem. And it also needs to be very fast and high performance because if this is in the loop every time Archie is thinking about something or making a decision or making a response, it needs to be very, very fast. And this is some of the advantages that we get from using SysML on a tool like Seaside. Just to give an example of this kind of fusion, this is a screenshot from Archie working on processing a customer spec for an air-cooled chiller. It's just really like these kind of one of these cocktail napkin kinds of specs where people give you like 12 bullet points of what they want in a custom design. And we had Archie analyze it and keep in mind industry standards and other things that might be relevant, and then produce a set of really well-formed requirement statements for us. And what Archie did was not just tell us what was in the customer spec, but actually compare and merge that with other considerations like not just things from the customer spec, but also things from ASHRAE and AHRI, industry standards organizations, from Manual J, which commonly tells you about environmental conditions and places some things might be installed, ideas from the EPA, and things like this, and gives us a set of what we really need to consider. In this case, for example, Archie identified that this chiller actually needs to have an efficiency of 10.1 BTU per watt hour versus the 9.6 from the customer spec, because that industry standard actually is higher and is more is the higher target that we need to meet, but still remembers where the information came from. Now, how does Archie interact with this mental model? Well, there are two kind of ways. One is direct manipulation, code editing. So again, since SysML looks like code, it's object-oriented. Some models like Claude actually already know about SysML v2. There is some direct manipulation we can do and direct synthesis of SysML we can do. And so we let Archie do that in some cases. But in other cases, the scale gets very large, or you really need to think about high performance. And so we use the same kind of tricks that AI coding agents use, which is to also bring in tools that are specifically designed for the programming language you're using to help you deal with those things at scale. So we would do things like design rule checks or semantic linting, if you will, like, is my design well formed? Are there things that are not related together that should be related together? Subgraph closure extraction. So if I'm developing a cooling system, maybe I could just get all the parts that are in my refrigerant loop and ignore the rest. Search. So instead of looking through all of that text, I could actually use a tool to do a faster, more thorough traversal. And then, of course, there's archiving and checkpointing for later recall. So if I am working with the system this week, but then I put that down and then I need to recall this context next week, well, if I actually have these things saved in a SysML format, then it's something I can save and then load back into Archie's context when I need it. And these are some of the advantages that we get from using an approach like this. We would have to invent it if it didn't already exist, really. So to recap what we're doing, Archie, our agentic AI, is designed to do cognitive automation of what the human does. And to do that, it needs to dynamically build an understanding of the system it's working on and the other context that is relevant, just like humans do. And the way we're doing that is using a scalable and high-performance graph, using SysML v2 and Seaside to build this understanding, and then to store and recall it for later. So that's what I have. Thank you again for the invitation, and thank you for your attention.
Thanks so much, Adam. It's really incredible things what P1 is doing, and it's great to see Seaside, playing a role, in this amazing technology development. And AI is a huge enabler, for all of us. So, any questions for Paul? So. Yeah, we have one question from Vince. Yeah, that's.
So my question is, how can you? Yeah, this will help for online people. So how can you make sure Archie has not made a mistake?
Yes, how do we make sure Archie has not made a mistake? So there's I'll list a few techniques that we've used. One is we've actually taught it a few techniques that senior engineers have told us they use with their junior engineers. So we're targeting like junior engineer level performance as a starting point. And one of these chief engineers said he's always talking to his juniors. When you get a result from a simulator, or you do an analysis, write down the governing physics equations and make sure that what you're seeing makes sense in that context. And one thing we've taught Archie to do is actually to do the same, to actually do a second type of analysis, to do a gut check, if you will, on the first one and make sure it goes in the right direction. This gives Archie the ability to self-correct. The second is that Archie won't be infallible. It will make mistakes, but our goal is that it's an error rate similar to or less than a human, such that if Archie produces a work product, you send it through exactly the same review process you would for a junior engineer on your team, provide feedback and revisions as necessary. And so we're also designing Archie to be able to explain itself, to explain its thinking, where it got answers, and so on, to support the human processes that are already in place.
One more question from Jasper, researcher at DLR, German Aerospace Center. How would Archie, would be better than traditional optimization techniques in design space exploration that are using more traditional optimization methods?
Mhm.
And why you're going AI route with LLMs rather than using more traditional approaches?
Sure. So I didn't really give a lot of biography, but I have spent a lot of time trying to build, well, successfully building, but model-based engineering systems that link together multiple representations of a design, link them up to optimizers and things like this. And those are very labor intensive and are very sensitive to small mistakes and things like this. And to build logic into traditional software that deals with all the little corner cases and edge cases and things like that ends up making your approach become very, very complex as well. And what is beautiful about this new wave of AI and about language models is that they're actually quite good at dealing with ambiguity and making judgments and noticing when things are weird or making corrections or things like this that allows you to do this in a way that isn't quite so sensitive to, making sure that you've taken care of every last corner case and edge case, which has been one of the things that makes it so time consuming and costly to build big multidisciplinary exploration systems.
Thanks so much, Adam. Incredible talk, and really exciting what you're doing. So everyone can check out online, P1, what they're doing, and they have really cool demos.